So let's talk through this first problem, number 20, and they suggest here that we write out the partial fraction expansion and that we don't go to that next step. That is to say, do not determine the numerical values of the coefficients. So, stop short of finding that a and that b, and certainly we're not taking any integrals at this point. So take a look at that first one. First of all, that denominator is factorable, and that's going to be one of the things that we're going to look for with these. That'll be a big clue. And we're going to take and separate those into two terms. So one of them is going to have the x plus 2, and the other one is going to have the x minus 1 as the denominator, and then those numerators for those two fractions, we'll define them as a and b. And we know that when we pull everything together, it has to equal that x up top. The next one, the b, notice that the degree of the numerator and denominator are the same, and this is where we need to pull off what I call the long division. And so we need to take that denominator and divide into that numerator, and the first term, x squared, goes into the first term, x squared, exactly once. And then we take 1 times that divisor, and we get x squared plus x plus 2. And then we subtract that from what's above, and we get a negative x minus 2. And negative x minus 2 is the remainder. Negative x minus 2, and we talked about how that technically should be written over the divisor. So the decomposition, if you will, is 1 minus, and now the remainder is going to be what? X plus 2 over x squared plus x plus 2. So it's going to be 1 minus, and then I wrote it that way. And then, I guess we could take that a step further, start thinking about how we would deal with that. And to x plus 2, there's two terms in that numerator that share that common denominator. So it could be written as 1 minus, well, an x over x squared plus x plus 2, and then I should say plus and that should be a minus sign in front of that. Both of those are going to be negative. This minus sign, and let me correct myself there, this minus sign is going to affect both the terms, so this should be a minus. Now thank God they didn't ask us to take this any further, because of course the first one, the integral, is x, and this next one isn't so bad because we can use the denominator with a u substitution, take the derivative, and we'll get 2x plus 1, and we can use that and fix the numerator in terms of a u du. This last one, though, we got a quadratic in the denominator, and boy, it's going to take some fancy work to get that third one done. So thank God they didn't ask us to work at that. So I believe that if we were looking or had answers in the back, that would be 20b, and 20a would look just like that. So hopefully you can do 19 without a problem. Let's continue talking about number 22, and I'll try to go a little quicker here. So this guy is equal to, and if we factor the denominator, we can see that it factors to x minus 2 times x plus and an x minus 3. And so those are the two partial fractions that we're in search of. So we might go off to the side and say, x minus 2 times x minus 3 is the common denominator, and that would force the numerator to be a times the quantity x minus 3 times b times the quantity x minus 2. And of course that's got to equal the original x minus 4, and that unfactored denominator x squared minus 5x plus 6. So focus on the numerator, right? The denominator is equal already. It's just the numerators. So I suggested to you that method of looking at the denominators and picking the zeros of the denominator, in this case 2 and 3. So what would that result in? Well, wouldn't it have a times the quantity 2 minus 3 upstairs on the left side, and on the right side wouldn't you have 2 minus 4, which is a negative 2, and a times a negative 1 equals negative 2 suggests that a must be 2. And then picking that other 0 of the denominator, wouldn't it be x equals 3? And if you put that upstairs, the a term would drop and you'd have b times 3 minus 2, and wouldn't the upstairs putting in the 3 give you 3 minus 4, or a negative 1? And then you've got what? 1b equals negative 1, which suggests that b must be negative 1. So now you're ready to write those two fractions with those limits 0 to 1, and the two fractions are, of course, 2 over x minus 2, and the second fraction would be a minus 1 over x plus 3, and x minus 3. And then let's split those to two fractions and work with them. So the two fractions, we're going to say the integral of the difference is equal to the difference of the integrals. So let's subtract the other integral, which is 0 to 1 of 1 over x minus 3, and then let's evaluate those. And so that first one, putting the 2 out front, will be the natural log of the denominator x minus 2 times 1, or just x minus 2. And the limits, of course, are 1 and 0. And then that second one, won't it be the natural log of x minus 3? And that will be upper and lower limits. And that's absolute value again. Upper and lower limits are 1 and 0. Let's work with that first one, and if you put 1 in, of course, you're going to get the natural log of 1, and if you put 0 in, you're going to get 2 times the natural log of 2. And then let's do that second one, and if you put the upper limit in, you get the natural log of 2, and if you put the lower limit in, you get the natural log of 3. And then we can work with that if you know your rules of logarithms. Of course, the natural log of 1 is 0, and 0 times 2 is 0. And then, wouldn't that be the same thing as the natural log of 2 squared? So you could write it as 4. And then, you got 2 logs in that second grouping there. So, and there's a subtraction sign, so couldn't you write it as a single log and say it's the natural log of 2/3? And now there's a negative sign in front of both. So in the next step, you might want to say, well, let's factor that negative out and write natural log of 4 plus natural log of 2/3, and then let's write that as a single log. So wouldn't that be a negative sign out in front of, and wouldn't you find the product of 4 times 2/3, which would be the natural log of 8/3? And that negative sign out front, doesn't that mean it's the natural log of 8/3 to the negative 1 power? And 8/3 to the negative 1 is 3/8. So there's a lot of trickery there, or a lot of review of logarithm stuff, as well as the partial fractions. Let's look at the next one. So let's take a look at number 24. And number 24 is a very standard kind of problem. Notice the degree of the numerator and denominator are the same, so aren't the same rather. So there's no long division involved here. The degree of the denominator is greater, and so and then we look at that denominator and we begin to see that, geez, that factors to x times x minus 1 to x plus 1, right? So we could break this into three partial fractions, we call them. So that denominator is x times x squared minus 1, and of course that's the same thing as x times x minus 1 times x plus 1. So let's go off now to the side, you might say, and say, well, geez, if the numerator on the left is x squared plus 2x minus 1, then on the right, wouldn't we have, if we utilized, if we brought back the common denominator, wouldn't x go in exactly x minus 1 times x plus 1 times? And then the second denominator, wouldn't it go into the common denominator, x times x plus 1, and we'd multiply that by our b? And then finally the third denominator, x plus 1, won't it go in exactly x times x minus 1 times, and we'd multiply that by our c? So remember that little trick we talked about, that denominator, what are the zeros of that denominator, and aren't there three of them? Namely that x could be 0, x could be 1, x could be negative 1. So let's put 0 in that left side, that is x squared plus 2x minus 1. If we put 0 in there, doesn't that suggest that the left side is a negative 1? And if we go to the right side and we put zeros in, well, these two terms will drop out, and all we'll get is a negative 1 times a. So if negative 1 equals negative a, then that suggests that a has to be equal to 1. And then if we put 1 in, won't our first term be 0, and won't our last term be 0, and we'll get in the middle here 2b, and on the left side, won't we, when we put 1 in, get 1 plus 2 minus 1? So won't we get this expression, won't we get 2 is equal to 2b, and therefore b is equal to 1? And then finally, one last time, on the left side, if we put in negative 1, won't we get 1 minus 2 minus 1 more? Well, we'll get a minus 2 on that left side, and on the right side, when we put in a negative 1, the first and second terms will drop, and then we'll get what? Negative 2 times a negative 1 will be a 2c, and if negative 2 equals 2c, then of course c must be a negative 1. So after all of that is said and done, and gosh, we have said more than we've done at this point, let's think about this integral, number 24, is really these partials with a, b, and c now installed. So to work this problem is quite doable, right? We're going to say, well, the integral of 1 over x dx, and then we're going to say, well, add to that the integral of 1 over x minus 1 dx, and then subtract the integral of 1 over x plus 1 dx. And those are three little easy integrals, right? Natural log of the absolute value of x, natural log of the absolute value of x minus 1, and minus the natural log of the absolute value of x plus 1 plus c, of course. We can combine those first two to a single log, take the absolute value of x times x plus 1, x times x minus 1, and then we're still left with the natural log of x plus 1 plus the c, but now we can combine those two again, and now it's going to be the natural log of 1 over the other, right? So it's the natural log of the absolute value of, in the numerator, x times x minus 1, in the denominator, an x plus 1, and there she is, right? Our final answer ready to go. One more time, and this last one's going to be a little more challenging. Number 26 is maybe a little more challenging than we want to go right now, but I'm going to just run through it quickly. First of all, those two factors in the denominator, x squared plus 1 and x squared plus 4, they're what are called irreducible quadratics. They do not factor, and therefore they command numerators in the partials of 1 degree less. So if it's x squared plus 1 in the denominator, it's going to be an ax plus b in the numerator. The same thing is going to happen with the second term, irreducible, the x squared plus 4, so the numerator has to be of that form, something x plus something, and we're going to use cx plus d to distinguish everything. So on the left side we have 2x squared plus 5, and on the right side, and this is where it gets a little messy right now because we can't come up with those zeros for the denominator, that little trick. So if you look on the right side, if you pulled things together, you would have ax plus b would have to be multiplied by an x squared plus 4, and the cx plus d would have to be multiplied by the x squared plus 1. And then if you did the FOIL, and that's what's happening here on this next line, I'm simply doing the FOIL of, ax times x squared is the ax cubed, and then the outsides gives me that 4ax, and the insides gives me the bx squared, and the last times the last is the 4b. And then I'm doing it all over again, the cx cubed, the outsides, the insides, and the lasts, right? And then what am I doing? Well, I'm saying, there's some x cubes here, there's an ax cubed, and there's a cx cubed, so I'm going to pull the a plus c together and make my total number of x cubed. And then my squareds, well, I got a bx squared and a dx squared, so a b plus d is the number of x squareds that I have. And then I'll come back and say, well, I've got 4ax and a cx, so together that makes 4a plus c x's. And then one last time, I've got a 4b and I've got a d, and together those make my constant term, right? So if I revisit my left side, my numerator of the problem, I have 2x squared plus 5. Or you might more properly say 0x cubed, 2x squared, no x's, and 5. So this is what we use as we begin to solve the problem, that a plus c, the coefficient in the x cubed, has to equal 0. And I'm coming here to the middle, right, and I'm focusing on all these coefficients, and then I have the next one, b plus d. Well, that's got to equal 2x squareds, right? So the coefficient has to equal 2. And then the 4a plus c for the third term, well, that's got to equal 0x, so 4a plus c is 0. And then finally, the constant 4b plus d has to equal 5. And so the first equation and the third equation are written in the variables a and c. Two variables, two unknown, or two equations, two unknowns. Let's use those first two, the first and the third, and we'll take the first one and say, geez, if I take c to the other side, I find out that a equals negative c. And then I'll carry that quantity down to this third one, and I'll take the a out, and I'll put a negative c in, and I'll get c minus 4c must be 0. And well, lo and behold, a and c must both be 0 to get that system made up the first and third equations to work. And similarly, if I take the second and the fourth, you have two equations and the two variables are b and d. So the second equation suggests that b equals 2 minus d. If we put that into the second equation that we have, that is the last one, 4 times 2 minus d, in place of the b plus the d has to equal 5, and then solve that out, and we find that, well, d has to equal 1, and then if we put it back into any one of them and solve for b, we get that b equals 1. So once again, a lot of fooling around to find out that the decomposition, when we put in our A, B, C, and D, we get this line right here, these two integrals, which are pretty simple integrals. That first one is that so-called Dan Williams integral, inverse tangent of x. The second one we'll come to see as a form when there's a 4 on the end. It'll be of the form x squared plus a squared, and it's 1 over a, or in this case 1 over 2, times the inverse tangent of, and it'll be x over a, in this case x over 2. That's going to be a form. We'll talk about that one, and then plus c. This problem could be done with integration by parts, but we don't want to do that. So that's it for these even ones. That's as far as I'm going to go with these examples. Have a good evening.